Okay, today's lecture is a continuation sort of what we worked on last time. Just talking a little bit more about simulation and modeling and when it makes sense, when it doesn't, some of the characteristics to look for in a model. And then we'll get in a little bit to some of the arena stuff. I'll work through a couple of sort of straightforward examples of simulation models and some of the mechanics of using arena, and then hopefully we can get a assignment put together for you to model for next time and start to get used to the software. I'm assuming everybody has installed arena on their laptops. I've not heard contrary to that. If you have had trouble doing that, please send me an email or give me a call on my cell phone, and maybe we can work through it on the phone. Otherwise, we can try to meet sometime if you're local to the area. Otherwise, we'll have to do it on the phone. But point being is we're going to really start to use that software, every class period and every assignment, which will be pretty much every week. So it's important that you get that installed. So if you had any issues, please contact me in some way, and we'll figure out some way to get it installed on your computer. So we talked about simulation a little bit last time and a little bit the time before, about when to simulate and when not to. And basically the rule of thumb, I guess, is that if you can create a valid model of a system that you can model analytically, in other words, you're getting exact results, you've got closed form equations that give you results for whatever the system is that you're trying to work with, then you wouldn't simulate. There's no reason to try to come in and establish statistical distributions for any aspect of the process if you have exact closed form equations that describe every portion of it. So that's sort of the rule of thumb. The thing with that is, of course, is that unless it's a really simple system, which then would give you a fairly simple model, you're probably not going to be able to do that. Most real world systems just aren't like that. If you think about pretty much anything that will work with manufacturing processes are going to have some natural variation to them. Even an automated process where you're getting some result, maybe a part being made or a part being assembled, you're going to have pretty good consistency in terms of part-to-part timing, but there's still going to be variation, part shortages, machine breakdowns, things like that come into play, and those need to be looked at as well. And it's pretty difficult to have a closed form equation that would allow for variation in, say, shipments of components or machine breakdowns, power failures, snowstorms, whatever it might be. So even something like that, where you've got a truly automated system and the timing is such that, with great consistency, you're getting a part every, 15 seconds, 2 minutes, whatever the time is. Even with that, there's going to be areas where modeling and simulation would be appropriate. Now, in that, though, as I mentioned, I think the last time, we can establish statistical models or probability distributions that utilize that data that you have. So it's not like you would throw away any data. If you're looking to model, maybe you're going to make a change to an automated system, maybe you're assembling cell phones, say, and you've come up with a better way to do it. Any areas that you haven't changed in the existing process, you would want to capture all the data you can on that and utilize that in your modeling. You wouldn't want to make assumptions if you've got data that you can use. So that's sort of just an overview of when it makes sense and when it doesn't. The other thing that needs to be mentioned and you need to be aware of as you're modeling systems, that if you have a very complicated system, it's sometimes sort of tempting to oversimplify. So you can get to something that you can basically do, that analytically that you can manage. So the advantage of that, of course, is that you got some answers with no uncertainty or noise. But the question you have to ask yourself is, how good is an exact answer to the wrong model? And that's sort of a question we need to ask. As we create models, we're going to get answers. There's no question about it. But you need to look at the model to make sure that it, in fact, does represent the system as it stands. So there's a couple different ways that you can do that. One is to just tweak the model a little bit and say, well, I'm assuming that I'm going to have a uniform distribution of customers coming into my fast food restaurant. Well, break the system a little bit and say, well, okay, I've got a uniform distribution, but maybe I don't. Maybe I'm going to have some hiccups here and there where I've got a busload of people coming in that I'm not anticipating. So when that happens, you need to be able to deal with that. And again, basically pushing the model to see how robust it is and how valid your distributions are. Is a really important thing to do. I mean, running the simulations, that's pretty much, the easy part. So the difficult part of this really is not so much the software or getting the right answers out of the software. Like most analysis programs that you'd use, whether it's a finite element analysis or something else that you might use. The key is to get good data in. And in this case, it's to get data that actually represents the physical model or scenario that you're trying to simulate. So that's really where the time needs to be spent, is to make sure that, the stuff we do in class is sort of, cooked up, scenarios. But when you're working on a real problem, the bulk of your time is going to be spent on really understanding the inputs to that system and the variability that can occur. So that's really where your time's going to be spent. Again, it's better to have, to solve the right problem or the real problem, not come up with an unrealistic model that maybe you get some exact answers, but they're not to the right model. So that's an important point. And we need to work on trying to test that a little bit too. You want to see how robust your simulation is by tweaking it, either changing some of the input parameters to the extremes that you might think they might be, or looking at the distributions, the statistical distributions that you're using, and seeing what happens if you change them. And we went through the statistics portion last time, or at least a little overview of statistics. And so hopefully you have a reasonable understanding of that, and that should have been mostly review, I think, but that's the kind of thing you really want to look at. So when do you simulate and when do you not simulate? If you've got statistical estimates with uncertainty and noise, that can be problematic. So you need to analyze your simulation experiments such that the activities provide a sound simulation that's sort of interwoven with the model that you create. And we need to, if we can, to try to measure that level of uncertainty and the noise that's in the system, to take steps to reduce it to a tolerable level, or make sure that the impact on your results or your answers that you get from the model, minimize the impact on those. So that's again another important point. So again, just sort of another way of saying it, it's better to get a sufficiently precise estimated answer to the right model than an exact answer to the wrong model. If you get the wrong model, you're sort of starting off on the wrong foot. Even with the same model, you're going to get slightly different answers as you run it. And that we'll get into this a little bit more, but that gets into replications. And replications are basically the number of times you run the simulation, and this is all programmed in. You program this in with a variable into Arena is important, because you need to make sure that you're getting a statistically valid answer. In other words, that you may have 3 or 4 or more distributions all interacting with each other in some way. And so as those distributions vary, right, from one value to another, and then interact with each other, you're going to get different answers. And that's the thing you need to focus on with the statistical, to make sure you're statistically valid. And there's tests that Arena has built into it that help with that. So you can do that without too much difficulty. The other thing is you're going to get different orders of processing at times. If you've got multiple paths through your model, you may get different timing based on what's passing through those different lanes or channels, if you will. So the quote here: simulation is no longer the method of last resort to be used only when all else fails, and that was from 1969. The simulation methods have changed pretty significantly since then, but it's still a good sort of a good adage to pay attention to. So again, some of the project objectives in a simulation project: you've got various sort of people involved in this. A stakeholder is just someone who commissions, funds, or uses or is affected by a simulation project. And where that comes into play, if you're working for a company and you're working in a operations research or maybe in some sort of industrial engineering function, you may get, not that you're going to get commissioned, but you may get internally funded by someone else in the company who's got an interest in, do I build a new plant, or do I expand this product line in some way? And simulation can be very helpful in that, especially if you've come up with a new manufacturing method that you're trying to compare to an existing one. Simulation can be very useful in doing that. And again, we talked about this the last time. The ideal solution would be, yeah, go ahead and build a plant and see how it works. But economically, that's certainly not advisable. So the simulation sort of takes the place of that and allows you, with just, again, some software and some time and some understanding of the data that you're looking at, come up with some pretty reasonable, useful bits of data that can help with decisions like that. So again, there's not really one single simulation model for a system. If you're working on something that is fairly complex and that there's a lot of dollars riding on, you're probably going to come up with several simulation models for a given proposed system, and then look at the variation you see in the data coming from those models. If you see little variation, chances are you're maybe on the right track, because you've got several simulation models of a system using different assumptions and whatnot. If you come back with reasonable answers from several models like that, chances are that you're sort of on the right track. So that's an important thing. Of course, you want to look at what are you really trying to learn, what are you trying to evaluate, what do you hope to prove. I'm building a manufacturing plant. I want to use a different process, one that I've not used before. So that would be sort of the objective of your project. The scope needs to be evaluated. Any kind of project planning effort, you need to look at the scope of the project and define it. Not maybe so much with simulation, but it can apply. You need to be aware of something called scope creep, which I'm pretty sure you've been exposed to in your project management classes, where really what that is you define the scope of the project, you start to simulate it, and the scope tends to creep on you. You start to say, well, let me include this, or let me include that, or let me expand this in this way. And sometimes that's okay, but you need to be aware of what you're doing, that you're making things more complicated, and you need to look at it and say, is that additional data points that I'm going to get, is it worthwhile? Is it valuable? And that's really that's really the question you need to ask yourself as a operations research or industrial engineering person. And then, what kind of form do I want the results in? What am I really looking for? Am I looking for a yes, no on a given process? What am I really trying to get? And I guess the thing that you sort of need to be aware of is, in fact, that all models are wrong, because they're representing reality with some assumptions, simplifying assumptions that you made. Earlier I said you don't want to oversimplify, but you do need to simplify to some extent. And the key is to simplify the things that aren't going to have a big impact on the final result. And that's really the key to a successful model. So one of the first aspects of doing any kind of simulation, in fact, any kind of project really, is to determine and establish a functional specification for what you're doing. And I don't know who said this, could be Yogi Berra, If you don't know where you're going, how will you know when you get there? It sounds like a Yogi Berra quote, but I'm not really sure who said it. And then the classic carpenter's advice: measure twice and cut once. So that's good. That's good advice. I mean, a functional specification basically is a document that describes exactly what you're going to deliver, when you're going to deliver it, how you're going to deliver it, and who's going to do it. So in a simulation project, that's a key point, because and then this needs to be sort of run by your stakeholder to make sure that you're giving them what they want. If they want to know, production capacity, and you're not focused on that, you're focused simply on ability to do changeovers or whatever it might be with a manufacturing process. You need to make sure that everybody's in agreement that this is what we're going to do, this is how we're going to do it, and this is who's going to do it, and this is when it's going to be done by, before you start, before you get too far with it. So rough numbers, and again, really depends on what the project is, but you could spend up to 10% of a project time on developing your objectives and your functional specifications. Sometimes it won't be anywhere near that much. Of course, depends a lot too on how similar is what you're doing now to something you've done in the past. As you do more and more simulations, especially in a manufacturing operation that maybe is making similar products, you're going to get a lot of, your body of knowledge is going to increase significantly as you do more and more of this stuff. So establishing that functional specification can become significantly easier as you've done more of it. So for most models, you're gonna return the objectives, a system description, your approach to modeling, maybe get into some of the statistical distributions you're going to look at. How am I going to best approximate the real physical system? What kind of input data do I require? What data is available? That's the other question to sort of ask. What data on a similar type process is available for analysis? And then plug that into your simulation if you can. Don't just rely on picking a statistical distribution. If you've got real data, utilize it in any ways that you can. What type of experimentation are we going to do? How are we going to vary the inputs to the system and then measure the results? And then finally, what are my deliverables? What do I expect to deliver from this project? Okay, so you've got a functional specification. That shouldn't really be confused though with how I start doing modeling. Most times you're not going to model the entire system and then hit the run button. You're gonna sort of sneak up on it, if you will. So the key is to come up with an overall, if you can. Many times you can come up with sort of an overall system model and have some sort of black boxes that things go into and things come out of, to get the thing to run and to get sort of establish. It's somewhat like software that you want to establish something that'll run, that'll execute, and then build on it. Maybe you take the black box, which you've got just as sort of a random process, and you expand that to multiple processes, multiple decision points, inspection points, maybe queues, whatever, and then build on that. And like anything else that you do, save early, save often. That's a really good adage, especially with software like Arena. It can be a little flaky at times in that it will lock up and basically shut the software down. It seems to be a little bit better the last version that I downloaded than previous, but it still does it occasionally. So get in the habit of clicking the save button before you hit the run button. So at least if the thing crashes, you can pull something back. And again, as I mentioned, use an iterative process to build your model. So you're going to add features and components as you go. Start off with sort of looking at an overall sort of black box kind of approach, and then build on that. And then run it, test it, repeat it, do some robustness testing, that kind of thing. So again, even just looking at this from a sort of a flowchart standpoint, you've got a simulation process model, your sort of basic functional blocks here. You've got the conceptual design portion, you've got input analysis, you've got model development, verification, and validation. Then finally, your output analysis and experimentation. And this is very much closed loop. you're gonna tweak and sort of cycle through this in an iterative kind of process until you get to something that approximates your actual physical model. Okay, so one of the aspects of using Arena and discrete event simulation in general, not just Arena really, it ties into queuing theory. Now queuing theory is sort of a methodology onto itself, but we utilize it in discrete event, and I thought it'd be useful to sort of run through what that is. I think it's somewhat intuitive, but we'll just spend a couple minutes on it. Sort of the basics of queuing theory, because it is pretty important to utilizing Arena. So most simulations are in some way utilize queuing system methodology to establish what they're trying to do. Essentially, what we're looking at is entities, could be customers, could be parts, could be whatever, are input or introduced into the system. They come to some processing point where they're waiting for service. If there's other entities, customers, parts, whatever it is, are in the process and are utilizing, have captured, or are utilizing the resource, they basically wait for service. In other words, the line at McDonald's would be an example of a queue. So once that the entities, customers, whatever, again, are serviced that are in front of you, then it's your turn. You get served. Maybe go somewhere else. Maybe you go to a different line. Not so much in a fast food place, but if you think about like a TSA line at an airport, there's several distinct queues that you'll get into, where your initial check of your documents, then you go to another station where they do a more thorough check, then you go to another station where you put your bags on a conveyor to go through a machine to be x-rayed. Maybe take your shoes off. You don't have priority pass through from TSA. Maybe take your laptop out, put that in a separate container. Then you go to another queue where you get you stand in front of a machine that's going to check you personally to see if you have anything that potentially is a problem getting onto an airplane. So again, that's another queue. You leave that, then again you go to another queue and you wait for your stuff to come out of the x-ray machine. So you've got 4 or 5 distinct processes or distinct points in that service of getting into the airport, or getting from the public portion of the airport into where the gates are. So that's a really good example of a queue, and we did a bunch of different simulations on that. It fits really well into what we're trying to do. But some of the examples, manufacturing is a great example of a place where simulation is a real benefit. Your customer in that case would be parts. Could be raw materials coming in, maybe 4, 5, 6, 10, whatever different processes take place with that part. Then maybe it gets assembled to another series of parts to make a final assembly. So those customers are your parts. Those would be your entities. In the case of Arena nomenclature, customers can be thought of as entities. Your resources, or your servers, would be, in that example, machines, people, transport systems, and so on. Another good example is an urgent care clinic. In that case, your customers would be patients. Your servers or your resources would be doctors, nurses, other medical staff, and also rooms. That would be a holdup in an urgent care clinic. You'd have a certain number of examination rooms. Once those are full, you may have doctors available or nurses available, but you don't have rooms to put the people in. So that's another resource that you would look at. And as you establish a simulation of that type of urgent care clinic or a hospital ER, that's one of the things that you look at. It's not just the people, it's also the physical space to put the patients, again, which are your entities, into. Supply chain, another great simulation application. Your customers in that case would be parcels. If you're shipping something from the post office or UPS or FedEx or whatever, the boxes and envelopes and whatnot would be the parcels. Loads would be those parcels sort of batched up together into a load that will go on to a truck. The trucks may also be looked at as entities that are filled with a load. So a bunch of different ways you can look at that, but one way would be that actually those trucks accept those loads and they become your customers. They would also be looked at though as a resource, because again, it's a finite number of trucks that you have available. Maybe that can be easily expanded by going to a truck rental company and getting a couple extra trucks on a day's notice or less, an hour's notice. But typically it's looked at as a finite resource. Warehouse space and loading docks, again, would be two additional resources that you would look at. You need the space to put the stuff. You need the docks to unload the trucks and load the trucks. Those would be finite resources as well. And again, an example in this type of a simulation, trucks, again, may be easier to get. If I'm looking at a resource, I may plug something in to say, well, I can, within a 2-hour notice or a 4-hour notice, I can get additional trucks. Probably can't get additional warehouse space or docks that quickly. You may be able to get it, depending on where you are. You may be able to get it in a week or maybe less, but probably not as easily as you can get trucks. So as you look at resources, that's one of the things you look at. If you get, and that's part of the robustness testing of your simulation. If I've got an absolute critical resource, maybe it's warehouse space, maybe it's docks for loading and unloading, how easy is it to get additional resources in place? Can I do it in a day? Can I do it in an hour? Or is it going to take longer than that? In a manufacturing operation, same thing with the first example we looked at, where you've got machines. I probably can't get machines in a day or a week. It's probably months. It's probably 6, 8, 10 weeks, something like that. Where people, I may barrel flex people from one operation within my plant to another operation. So I may be able to backfill resources or people resources easier than I can machines. So again, that's something you look at in a robustness test. How hard is it to blow up your simulation? Another system, and this can be looked at a couple different ways, is a bank. Your customers, again, would be your customers, your bank customers. Your resources would be your tellers, your loan officers, your drive-throughs. And today, maybe more importantly, would be things like call centers and things like capacity of your computer systems to handle e-transactions, right? I mean, many people today don't. In fact, I haven't been to my bank in probably a couple of years, actually, but because we do everything electronically. So the resource there is not really the tellers that are in that office. They don't impact me at all. It's the ability to handle a transaction electronically, and that can be a significant thing, something that can be flexed up and down, possibly easier than a teller would be or a loan officer, but still, or drive-through, physical drive-through, but still needs to be looked at as a resource and needs to be managed. Just a couple other examples. An amusement park, obviously your guests would be your customers or your entities as we look at it in arena nomenclature. Your resources or your servers, again, would be the rides in that amusement park, food stands, urgent care clinics, things like that. Restrooms would all be things that would be looked at. You don't want to have a line of 100 people in front of a restroom or a food stand or a ride. And that's can be managed in a bunch of different ways. One of the ways that, for example, Disney does it is they have priorities that you can establish. You can let them know that you want to go on a specific ride roughly at this time, and you can get a priority pass then. So that's one of the ways that they manage that. If you can plan your day a little bit, you can spend less time standing online than you would otherwise. Another example, computer labs. Your customers would be students, your entities would be students. Your servers, again, would be the physical hardware, as well as the help IT staff to get you going if you can't print something or your computer locks up or whatever. Telecommunications is something that I think I'd like to look at a little bit this semester. We've not looked at that in the past, but it is a very important piece. The customers in that case would be data, basically, the messages or packets or files or whatever traffic that you're pushing through the pipe, the internet, or whatever telecommunications, some proprietary, or not proprietary maybe, but internal network, not maybe the public internet. Although today everything is pretty much on the cloud, and that's going over public internet pipe. So that's something that's looked at. Your servers, again, it'd be your your hardware, your terminals, your switching systems, routers, things like that, as well as the support staff to keep those up and running, as well as things like emergency backup power, large internet routing locations have backup power that needs to be looked at in terms of its capacity, in terms of its reliability, and needs to be part of a simulation. So that one could get sort of interesting, and I think maybe we would look at that. There's a lot of things you could throw at that to make your system sort of go in different directions. And then finally, infrastructure in terms of traffic could be automobiles, could be people, could be railroad, could be subways, could be whatever, could be airlines, could be almost anything like that, where you've got customers of some sort. In that case, vehicles or people would be your entities. And then infrastructure would be how many roads you have, how much space is there, in a given intersection, how readily does it expand? Is it single lane? If I'm looking at an automobile intersection, is it single lane coming in all directions, or are there multiple lanes? That's something that is probably the hardest of the stuff we've looked at so far, probably the hardest to expand resources quickly. It takes a long time to build another airport runway, or to build another train line, or to build another road or highway, whatever. So that's one that there's creative things that can be done, but to actually physically build additional hardware, that's not something, or not hardware, but infrastructure. That's a pretty difficult thing to do. Okay, so if we look at a single server queuing system, real straightforward. Let's look at a medical facility of some sort, urgent care type center, ER room, whatever it is. So you can see from the graphic there, you've got arriving patients, and Arena, as we get into that, looks very much like this, or can be set up to look like this. You've got arriving patients arriving at a registration desk. You've got a queue. In this case, you can see 3 patients, the 3 yellow dots, that are waiting to get to the registration desk. And you can see that there's a patient, a yellow dot, is at the registration desk, which is shown by the blue square. So a typical station or typical queuing system that we look at, when there is an entity, in this case a patient, occupying a resource, in this case the registration desk, no one else can occupy that resource. That resource has been seized, and until that entity leaves that resource, it cannot be used by anybody else. Now we can set it up differently from that, but that tends to be the sort of the easiest way to do it, and to manage multiple resources as separate resources, rather than trying to come up with a different way of managing that entity resource interaction. That tends to be the easiest way to do it. So anyway, then the output of that is you've got the patient gets registered, and the patient then departs. So the things that we need to look at are the inter-arrival times, and then the service times. So the service times you've got, in this case, this is just a single server station. My service time would just be time to register the patient. And as you can imagine, sometimes it's going to take more time than others. If the person doesn't have all their documents, or they can't find their insurance card, or the insurance card they have is expired, and the person needs to find one, somehow find their registration online. All that can affect the person who walks up with insurance card in hand and any other documentation. If they're there for a test or whatever, they've got all the documentation, the order from the doctor, everything is in hand. They're going to fly through that registration desk, at least in comparison to somebody that walks up and doesn't have that. They forget their doctor's name, and they forgot their insurance card, and they forgot the order from the doctor. So that they may get sent away, or they may end up spending 4 or 5 times as much time with that person to get get them serviced. So all those things need to be, again, either through some actual data that you may have on a similar station, something like that. You could probably find some data on. Maybe you'd even do some informal testing or observation in another facility. If you don't have any of that, you're going to have to pick a probability distribution. If you have some of that data, you can sort of fold that into the simulation and have a simulation that's probably a little bit better than one that wouldn't have that. And then what we're interested in is some output from that, some kind of metric or performance measure of the output. Things like total number of patients going from arriving patients to departing patients. In other words, how quick or how many patients did we process from entry to exit over some period of time, be it a shift or be it an hour or be it whatever it might be. Another metric that you look at that is somewhat dependent, but also somewhat to some degree independent of the number of patients, is the average time in the queue, not counting the service time. So how long did that person have to wait before they got to be serviced, right? Another one is the maximum time in the queue, and this is an important one. Average time in the queue may be low. Maybe it's 2 or 3 minutes if most of the people got serviced in a 1, 2, 3 minute time frame. But then I got a person in and it took 30 minutes to get them processed. So my maximum time in the queue might wind up being, if there's 3 or 4 people in there already, might be 35 or 40 minutes. That may be a bigger problem in terms of the overall process than the average time in the queue. If I go, and I'll use the example, and I think I might have said this one before, if I go to a McDonald's, my expectation is that I have my food in 3, 4, 5 minutes, 6 minutes, somewhere in that time frame, I would guess. If it's 7 minutes, I'm probably not going to get upset. If it's 8 minutes, I'm probably not going to get upset. If it's 45 minutes, I'm probably going to leave, right? So that maximum time in the queue can be depending on the characteristics and what makes your process, whatever you've chosen to simulate, whatever that process is, what makes that work and make that not work in terms of your in your customer's eyes. And that's how you need to look at it. And also critically important on that is, what do I do to mitigate that? If my McDonald's example is such that, again, for whatever reason, I've got a 45-minute time in the queue, either I'm overloaded because all of a sudden a busload of people pulled up, which is a perturbation of the system that I haven't really thought about or dealt with. How do I mitigate that? And that get well plan, and that can be simulated as well. I pull in additional resources. I can pull people in easily, probably. I probably have people that are doing other tasks at McDonald's that I may be able to pull in and put them on a counter to get more orders going quicker. How do I manage that? And then test that again with your simulation. This is a good example of where you would start with a fairly simple simulation. And then as I look at things like maximum queue time and what happens if all of a sudden a busload of people pulls up in front of my store, my restaurant, how do I manage that? And then implement that in your simulation and see if it actually works. So the time average, number of parts in the queue, in other words, the number in the queue divided by the length of the time period, another characteristic to look at. Maximum number, in this case, of patients. I keep going back and forth between this and McDonald's. So the maximum number of patients in the queue over a fixed time period, the average patient time in the system, maximum patient time in the system, again, 2 very different things, and probably a different tolerance of that customer. The whole key with this or with fast food or manufacturing or whatever is to have a happy customer at the end of the day, right? So you need to look at what makes a customer unhappy and then deal with that. And this could be a node. It's shown here as a single server queuing system is how I'm looking at it. But this could just be a node in a larger network of systems. And we'll look at that a little bit as we get further on. But this is the kind of thing you'd start with and then expand upon it. Expand. If I use my airport example where I've got 4 or 5 distinct processes with their own resources, which can maybe be bounced around in terms of people. But this would be sort of the starting point of that, and then expand upon it as you go further with it. So if we take the single server queuing system, and we expand that network together, different operations or different processes that would follow each other. We can wind up with something like this, which is sort of a quick network view of an urgent care clinic. The assumptions that we make going in are that there's random arrivals. In other words, there's no appointments for this urgent care clinic. And there's branching probabilities. The branching probabilities are independent. In other words, there's no dependency between whether you go right or whether you go left. It's simply based on what information you would provide at the sign-in station. So that's the assumptions. Some of the questions that we might ask, how many staff of which type do we need during which time periods? Many times processes like this are very much dependent on what time of day you're in, especially with things like fast food. Obviously, breakfast, lunch, and dinner, you're going to be busier than you are at 2 o'clock in the morning. Probably same kind of thing with an urgent care clinic. They're probably busiest maybe in the morning, maybe in the evening, off work hours, not really sure. But that would be a piece of data that you could probably determine fairly easily as to what the busy times would be for a given simulation model. In this case, the urgent care clinic. So what we're showing here is the arrivals. These green dots are the entities or patients coming in. The sign-in process, you can branch in 2 directions here, either go towards registration, or if you've got something that appears to be more serious, you'd go directly to a trauma room, maybe from there to a treatment room for further treatment, and then some sort of exit path, normal exit out of the facility. If your condition is determined to be less critical, you'd go to a registration, then go to an exam room, then maybe go to a normal exit, or maybe to some sort of a treatment room. So you'd have a branching path coming out of each one of these processes. And that's shown here in the little icons and what they mean. So some of the questions again: staff, how much, during what time periods, how big should the waiting room be, how big should the treatment room be, how big should the trauma room be? All these different exam room, all these different areas require not just staffing in terms of doctors, nurses, and other medical staff, but also physical space. And how big does that need to be? And again, keeping in mind that typically it's easier to flex or increase and decrease staffing than it is to increase or decrease, in the short term certainly, physical space. Difficult to build a trauma room overnight, probably not impossible to get some short-term or short-time help in to help with overloads. So again, if we look at other factors, what would be the effect on a patient waits if the doctors and nurses tended to decrease or increase the time they spent with their patients? So in other words, how thoroughly do they question the patient? How much time do they spend discussing treatment? How much time do they spend in discharging that patient and giving them discharge instructions, things like that? So as that flexes up and down, what impact would that have on the overall, both on the overall time to get through the system, as well as maximum time and wait times and queues and things like that. The critical things that you see as being crucial or critical to the process. So what if you bumped up the number of patients by 10% that they arrived? The arrival rate, in other words, increased by 10%. What impact would that have? 10% is a fairly small number. You would expect to see some impact on performance characteristics, but you wouldn't probably be happy with blowing up the system entirely. So that's the kind of robustness test that you would do typically to a process like this. I've got something that runs nice and steady state, bump up the arrival time by 10%, see what happens. If it's a minimal impact and the system can absorb that fairly easily, then your system is more robust, obviously, than if it can't. So then the other question, and it's probably fairly clear in this example which would be the right one to do, but in other examples, should we serve patients in order of their acuity? In other words, how severe is their illness or injury? Or should we just do a first in, first out, FIFO? And this is more of an inventory kind of question. So probably not applicable to an exam room or an urgent care clinic. It's pretty, clear, I would guess, that if someone comes in with a very serious injury or illness, they're going to be treated prior to someone who's got a cold or whatever. Okay. Okay, so as I mentioned earlier, there is queuing theory is sort of its own methodology and somewhat separate from simulation. Queuing theory tends to be a steady state type system, longer run type things, where simulation models can typically deal with shorter term, more dynamic systems. So why do we look at both? Well, the simulation does make use of the queuing theory in some places, and some of the logic that we look at and some of the graphics that we look at are very similar. So it's worth, I think, spending a little time on both, and then our focus will be mostly on the simulation models. But I think it's good to get some background in the queuing theory as well. So in some cases with queuing theory, you can derive an exact closed form solution or formula for the outputs. In other words, I can take my inputs, I plug them into an equation or a series of equations, and output a series of performance metrics, expected performance metrics. And those match up very well with the physical model. So it's a closed form, exact solution. Simulation is not really fit into that very well. The simulation model, you're making assumptions, and sometimes you don't with queuing theory. So it's a different thing there. You're using statistical distributions to simulate things like service times and arrival times and inter-arrival times and processing times to a degree. So it's a different situation, but again, does use some of the queuing theory as well. So if we take our simulation model and we add some of these extra assumptions in it, we run it for a very long time, can we get the same sort of answers? And sometimes we can. Practically speaking, we really should. If we run it till we're statistically valid, so we've got a sufficient number of replications, and our assumptions and our simplifications and the distributions that we pick are valid for that physical model, we should get answers that sort of converge on each other. So that's just another sort of check. If you have the ability to use some closed form equations for even a portion of your model, then sometimes that's a useful thing to do and see how well the answers converge. So the queuing system structure and terminology, very similar to what we use in Discrete Event, specifically with the Arena software. One of the key characteristics or inputs to a system are the entities. And we've talked a bunch about this. It's things like customers, patients, jobs, parts, manufacturing parts, whatever they might be. And they arrive. One of the common things with any simulation that we do is we're going to have entities. Those entities, as I said, can be many different things, but they're going to arrive in a system. They're going to get serviced at either a single station or possibly at several stations, possibly sequentially or possibly in parallel. We can set up simulations such that as entities arrive into the system, they can go to parallel workstations, or maybe they get sequentially serviced. In a manufacturing operation, maybe you have a sequence of operations where maybe you mill a part, then maybe you drill a hole, then maybe you tap that hole. Maybe that's 3 separate operations. And then maybe I'm making another part in another parallel line, and I take those 2 parts now that I've manufactured and I assemble them together. So you can have multiple structures depending on what the actual physical model looks like. They may wait, typically are going to wait in queues in front of those processes. The way we, for the most part, utilize Arena, we use in the examples that we typically have done up to this point, do a seize, delay, release type format with each of the processes, and specifically with the resources within those processes. So when that resource is being utilized by an entity, or in some cases a batch of entities, it's seized and it cannot be used by anything else until it's finished. Then it releases the entity it's working on, and a new entity comes into place. in almost all the applications that we utilize, those entities do leave the system. So it's an open system. They get processed and ultimately leave the system. Most times in a different state than they were when they came in. There's been something done to them, some value added processes have been done to those entities, but they end up leaving the system. If they were to never leave the system, I'm not real sure what a good example would be of that, but you would term that as a closed loop system. So again, a queuing network, which we had an example of up here, the urgent care clinic, a network of single stations. We take several single separate queuing stations, which is a single or could be a multiple server queue. And then we combine those together. Again, could be in a parallel format, could be in a sequential format, could be identical in service speeds, could be different. Queuing tends to work with identical service speeds, much like you would balance a assembly operation. If you have an assembly line of some sort, and especially one that, well, even ones that are automated, you need to balance the operations between them, and you make assumptions such that you'll balance them to the point where each operation or each sequential server queue or server processing time is going to be approximately the same. So the queues tend to be the same as well, unless there's a hiccup in the system. So with discrete event and Arena specifically, we don't necessarily follow that. We're using, again, not using these closed loop formulas or equations like we talked about up here. We're using statistical distributions. So those will give us varying answers as the simulation runs. So again, that's a queuing, another sort of variation again between queuing system methodologies and simulations. Queuing system assumes that the servers all have servers or resources. Another word for servers would be resources, are identical in service speeds. Okay, so you can set your queues up, and this is common between the two methodologies, the queuing system and the discrete event simulation. The discipline that's used in the queue, in other words, when can an entity leave the queue and start service, which one gets to be the next one to be served. So there's a couple sort of common structures that can be used, and these are common to inventory. If you've worked in any kind of operations research and talked about inventory and how inventory is managed and the flow of product. First in, first out, or FIFO. In other words, the first product that comes into that queue is the first one to get served. Last in, first out. So in other words, the last part in is the first one to get service. So you can think about that. A sort of practical example of that would be if I'm grading papers, right? I start with the first one, I grade it, goes on the bottom of the stack. When I get to the last one, that winds up on the top of the stack. So when I disperse that inventory or hand out those graded papers, chances are that I'm just going to take and start feeding them off the top. So the last one in would be the first one out. And that is an inventory methodology. And there's various reasons sort of beyond where we're going to go with this, with this class, that you might use one over the other as you get into operations research and some of your other planning courses. You'll probably get into that a little bit more. And then another common method is to use priority, and we use that in Arena as well. We may want to establish a priority for a given part, and one of the places we used that last year was a couple places actually. One was we did some toll booth simulations, and we looked at people coming into the toll booth with an easy pass. They got a priority over the people who were paying with cash. So that was one place we used it. Another manufacturing example, we had a process that was performing a manufacturing process of some sort, drilling, milling, I forget exactly what it was, on an entity or on a part. And from there it went into a decide module which rejected some of those parts. Some percentage of the parts got rejected, and those got sent through a rework loop. And when we did that, we established a priority to that rework loop. So those got serviced first. So if they came into the queue in front of the process, they would go right to the head of the line and get serviced first and get shot back out again. The other thing we did with that similarly is we assigned an attribute to those parts that said that they had been reworked. And if they got reworked and got determined to be defective more than 2 times, they were ejected from the system. So we didn't allow them to continue sort of endlessly through the loop. If there was a manufacturing defect, we gave it 2 chances to get fixed in the primary process. But if they didn't get fixed during that time frame, then we would, during 2 loops through, then we would bounce them from the system. So just another example. Those are the 3 that we'll use in doing our simulations, priority being a very useful one. Okay, so the metrics that we look at performance metrics, and Arena has a capability of doing this. We can run a simulation and then it'll bounce back to us various metrics, some of which we can define, some of which are sort of included in the base package. And depending on what your process is, some of these may be more important than others. So one of the things you look at is time in queue, and that would be the time that you're waiting in line. That would exclude the service time. So the time in system, for example, would be the time in the queue plus the service time, where time in queue is just the time that you're waiting. And you can look at that for an individual station, or you could look at it for the overall network or overall process. And again, that can be a very important one. There's reasons why you don't want people waiting in line. Urgent care clinic would be one. If you have people that have a serious illness or injury, you don't want them to sit in the queue for very long. The service time, on the other hand, may be just required because of whatever they have. If they need to set a broken bone or put a cast on or whatever it might be, that probably is more acceptable than somebody sitting in a queue where they've not even been seen by a medical person. That would tend to be a much more serious thing. So again, depending on your process and what it is, these performance metrics have different value or different priorities in your simulation model. The number of entities in the queue, again, that doesn't include entities in service. That's the number of people in line. That can have an impact in a manufacturing plant as to where do I put all these parts. If I've got a queue, first off, I'm not happy because I'm building a queue of parts. I've got a lot of parts in inventory then in a work in process state, which isn't something you really want to have in a manufacturing operation. But beyond that, from a practical standpoint, I need to put them someplace. I can't just stack them endlessly up. In the computer system, they just stack up nicely, but in the real process, they're physical parts. So I've got to do something with them. Number of entities in the system could be important for certain operations, maybe from a floor plan standpoint. That I've got sufficient space to deal with them all, but that's everything in the system, everything that's in every queue over the entire network, if it's a multi-node process. So everything that's in the queue plus everything that's in service. And then the last one listed here is the utilization of a server or resource utilization. So from a manufacturing standpoint, again, well, I guess a number of different things, but specifically from manufacturing, that can be very important. You want to utilize your equipment. You want uptime on the equipment. You also want to utilize it as much as possible. You've paid a capital expenditure for a piece of equipment. You want to make sure it's being used to the maximum. So that's another thing you would look at is how much am I utilizing? What's the time that it's available? And compare that to the time that it's actually being used. Okay, so if we go back to our urgent care clinic and just sort of expand on that a little bit, we've got our arrival time, and what we did then is sort of break this down into some fixed probabilities, or fixed paths, really. 90% of the people, entities that arrive, or patients in this case, that arrive at the sign-in go to registration. 10% go to the trauma room. 100% or one would go to the treatment room. On the other path, where they go, 90% go to registration. 100% of those go to an exam room. 40% of those go out, exit out of the system entirely. 60% go to the treatment room, and then 100% go from the treatment room to the normal exit. The only variable, random variable that we have is X sign-in. So in other words, how many people are arriving at the system, and we'll make some assumptions for that. And again, this is queuing theory. And we talked about this, right? This was our example single server queuing system. Got the arriving patients, we've got our queue, patient being registered, this is the resource, this blue box here, and then finally our departing patients. So if we put a little bit more data to this and we look at patients, we have 10 patients that are coming in, and this is the arrival time. In other words, patient 1 arrives at arrival time 0, patient 2, 3 minutes in, 3, 4 minutes in, finally 10 and 38 minutes in. And then we've got our inner arrival times, okay, which is basically the difference here between these numbers, right? So in the first case, we opened the door, patient 1 came in at time 0, or that's when we started the clock actually. Patient 2 came in 3 minutes later, so the inner arrival time was 3 minutes. Here it went up to 7, here it went up to 9. So between 8 and 9, for example, patient 8 came in at 0 minus 26, patient 9 came in at 0 minus 35. And then finally the service time. And the service time is somewhat independent of the inner arrival times because that does not include the queue. So that's just what time it took to service whatever issue the specific patient had. So it went from 1 minute on patient 9, fairly simple thing, apparently up to 7 minutes on patient 6 and 7 minutes on patient 10. So again, some of the things we might look at, some of the characteristics of the system, the total simulation time, our average waiting time, our wait and queue probability, our idle server probability, our average service time between arrivals, average waiting time, if waiting, and then finally our average time in the system. So in this case, this would be done, or our way to do a simulation on this would be to use something like Excel. And that's sort of what's being done here. We've got some numbers plugged in here, some of the numbers that we've taken from up above, and then we're breaking that out into time service ends, time customer waits in the queue, some of these characteristics that we're looking at. And then all these things can be calculated basically from this raw data. Fairly straightforward averages and average waiting times, total simulation time. All those things can be calculated pretty readily from this. So again, we've not really put any statistical distributions in. This is all, basically closed form equations, exact closed form equations, where we've got some hard data that we're working with, and we just calculate basically the characteristics from that. And then we can, obviously graph that and look at things like total customers in the queue at various times. Again, we went from 0. In this case up to 45 minutes, which was, I believe, the 38 minutes plus the service time that last patient took. So our start time was when the first patient arrived, and our end time was when the last patient left. So again, hard data can utilize this. Very useful though in terms of, and you'd probably do this over a longer time period than just 45 minutes, but gives you some good data as to when you've hit a lot of customers in the queue. Is there some correlation between that time and time of day, or is it sort of random? Be something you need to collect, a little bit more data than what we've got here to ascertain. So we can also, look at some of this data in a couple different ways. We make some assumptions. We have a certain number of servers or resources within a single queue. We're using FIFO, first in, first out, in terms of how the queues get emptied. We've got our inner arrival times set as random variables. We've got our service times likewise set as random variables. In other words, there's no dependence on between these two. The arrival rate and the service time there's no relation between them. So again, their two are both independent of each other. And we look at some of the other characteristics. We look at the system utilization. And again, this is for queuing systems. We can look at some steady state averages, delays. We can look at waiting times, establish a number of customers in the queue at any given point in time. And we can do similar things with the discrete event simulation software arena. So this part is fairly similar to the kind of things we can look at. And then just some of the formulas that are used. Probability that the system is empty or idle. solid state average in a queue, system average, and this is calculated right from the data that we've got up above. So again, a queuing network consists of individual nodes, individual queuing nodes that we had looked at earlier. They're connected by some sort of connecting lines or arcs that represent entity travel. So in the queuing network, and similarly, there's different tools or constructs used to do it, but we can have entities arriving from outside the network, and we can have entities exit from any node outside the system. A little different using Arena. There, you need to use a dispose module to do that, but it's just sort of the mechanics of the system. And again, when an entity leaves a node, it can go out of any of the arcs or the connecting lines emanating from that node. Probabilities need to add to 1. So if we look at that, let's just take back up here for a second. If we look at that up here, what we're saying is that you're going to leave the exam room, and there's a 40% chance you're going to the normal exit, 60% chance you're going to the treatment room. So those two numbers, the decimal representations of those two percentages need to add up to 1. In this case, there's only one way out. In this case, there's only one way out. So the percentage obviously equals, or the probability equals 1. Okay, and there's various, this, not really going to get into this, but this Kendall's notation, there's another one down here called, I think it was Jackson Network. So these are just people that are, active in doing research and queuing theories, and they've come up with some of their own twists on how this stuff works, their own assumptions and their own sort of constructs and methodology as to how these things work. So some of the assumptions: arrival processes from outside have exponential inter-arrival times. In other words, they follow a Poisson process, and that they're independent of each other. Service times likewise are independent, in this case exponential. Queue capacities are infinite. Utilization, traffic intensity locally at each node is less than 1. So this is called the Jackson Network. Apparently the individual who came up with this was named Jackson. So we do similar things in Arena. Again, this is queuing theory, but similar type, in terms of what we're doing, at least similar type things. And again, this is just another shot of our urgent care clinic. So in this case, we can analyze each node as a standalone, or then combine them together into a network, which is sort of what we did. One of the, and again, this was just a sort of a subset of that, with some probabilities and the probabilities of going from one station to the other, as well as the service times being exponentially calculated. STB for the station, STC for that station. So that's it for this particular topic. I just wanted to spend a little bit of time on queuing networks, talk about it a little bit. There's a lot of similarities to what we do with Arena, and a lot of the graphical representations are the same. So what I'm going to do now is I'm going to pause here for a second. I think we'll wind up ending this video and starting a second one, because I need to switch over and get Arena up and running. So let me do that, and then I'll just spend a little bit of time putting a fairly straightforward simulation together. We'll just pick up a manufacturing process of some sort, put a little bit of graphics to it, and then just sort of run that. And then we'll talk a little bit about what I'd like you to do for next time, basically to put together some sort of a simulation and see where we wind up with it. So give me a second here to switch over, and we'll have a second video for you to look at with running Arena.